this particular presentation, I have taken more in particular of cargo pump on tankers, both oil tanker, chemical tanker, and gas tanker. As all of you are aware, the learning objective, as all of you are aware, the main thing in tankers, the cargo pumps, they to discharge the cargo within the stipulated time. We have a charter party agreement, and every tanker, the thumb rule, normally we say it's about 24 hours, say about a day. So entire cargo, irrespective of the size of the tanker, it can be a product tanker or it can be a VLCC or whatever is the capacity of the ship, still the cargo has to be discharged within the stipulated time. And invariably in all the type of tankers, we use centrifugal pump. So if you just go a little further, the learning objectives of this particular session, knowledge of pump theory and characteristics. Yes, I am going to briefly touch this because this has been discussed in detail in my last session. And pump performance curves, just I will show 1 or 2 slides. That again, how to make the curve we have already discussed. And the back pressure curve, or what we call shore curve, because when cargo pumps, we need to look at not only on the inlet side or the suction side of the cargo pump, as well as the discharge side, at what rate we are giving the cargo to the shore tanks. So that will decide when do we complete discharge. So usually the thumb rule, as I have said earlier, it's about a day, say about 24 hours. And very often we finish the cargo in 20 hours, 22 hours, sometimes even less than that. So the back pressure curve, or what we call shore curve, it varies from terminal to terminal, from one discharge port to another discharge port. And very often, in tankers, what do we see? If we had been to that port earlier, we also look at point what we call experience factor. That means last time when the vessel was here, how long it took. And a lot of input to look at the back pressure is given by the loading master also when we interact with him. Initially, before the cargo operation starts, the terminal representative, or what we call loading master, gives us a lot of input about that particular port. So that also we need to look at. But generally what happens, the loading master tells us to maintain a certain manifold pressure, say about 6 bar pressure or 7 bar pressure. And the cargo pumps, when we run, we maintain that pressure. But when we initially start cargo discharge, it's not a problem. But usually what happens, when you complete a tank, or that time you find it little difficult to maintain that pressure. So that time we move on, instead of 1 COP, we are running 2 COPs. That means we run pumps in parallel, sometimes 2 pumps, sometimes 3 pumps. So we need to have an idea about how to run pumps in parallel. So that also we will touch here. So in series and parallel, that's the 4th point there, principles behind running pumps in series and parallel. And in oil tankers, chemical tankers, and gas tankers. So these are all the things we are going to briefly discuss today in this session. So advantages and disadvantages we have already seen. Anyhow, we can just have a look at it. So the advantage of centrifugal pump, we always, in all tankers, we use centrifugal pump. Whether it is a gas tanker also, it is a centrifugal pump. Or a chemical tanker, or a product, VLCCs, everywhere we are using centrifugal pump. But the biggest advantage in centrifugal pump is with reference to the volume. The large volumes can be pumped. As I have, if you just look at VLCC, the cargo pump capacities may vary, 3,000 cubic meters per pump, or maybe up to 5,000 or even more. Now look at VLCCs and ULCCs. So if you run 3 pumps, so 3 pumps means about 15,000 cubic meter per hour. So in 10 hours, about 150,000. So in 20 hours, we'll be able to complete the ship. So that's how. So the compact, size, space saving, and large volume, steady output, maintenance, and no noise. These are all the points we have already seen So, but only thing is the disadvantages, if you see, again, this cannot handle air or vapor, because if you see your chemical tankers, we always look at pumps like Framo pumps or Marflex pumps, and this type of pumps are always, in the what we call submerged cargo pumps. That means the location of the pump is right at the bottom of the tank, so the pumps are always submerged. So meaning that the centrifugal, your cargo pump always gets a positive suction head. So as long as your suction head is positive, you don't have any issues. Whereas at any point of time, if the cargo level or the oil level goes below the, you can say, eye of the impeller, then you are going to have problems. So how much it can go below. Whereas in gas tankers, again, if you see in every cargo tank, yes, we have a cargo pump, that is deep well pump. There again, the cargo pump is kept in the cargo tank right at the bottom. So there again, till the tank is empty, because suction wells are there. So the cargo pumps are located more or less has an advantage in the suction well. So by the time the pump loses suction, you will see your tanks are empty. Whereas in tankers, in oil tankers, what happens? You have a pump room, and then your cargo tank. So the pump room, you have your COPs are located in the pump room. Whereas sometimes there is a possibility, initially when you commence cargo discharge is not an issue, but when you come down to the stripping level, when the oil level goes below the pump level, so that is the time you may need to look at your NPSH requirement, or whether the pump will be able to, keep the taking suction. So these are all the things you need to look at. Mainly chemical tankers and gas tankers, not an issue, because the pumps are located inside. And of course, some of the oil tankers also nowadays with Framo system, yes, we have the pumps inside. But in bigger ships like VLCCs or ULCCs, we have a pump room separate, being between your engine room and the last cargo tank. And that's where you may come across this issue. We will have a look at this. That's the main disadvantage with centrifugal pump. And of course, the pump basic concept is like this. So this type of volute casing, and in fact, if you just see, many of the higher capacity pumps are having double volute casing, which we have already discussed. So double volute cargo pumps, that is many of the cargo pumps of higher capacity is of that nature. So if you just look at this particular pump is from an oil tanker. So the capacity range of this type of pumps is about, say, 500 to 15,000 cubic meter, a total head up to 200 meter liquid column. So the speed of the pump, generally your COPs you will see up to 1800. Generally you will see 1200, 1400. And here it is a centrifugal pump of a tanker, what I have shown. And of course, it's usually you will find this type of bigger capacity pumps are what we say double entry pumps, double entry cargo pumps. And this is how it looks like. And it's the same thing, but a schematic diagram. So double entry, so that makes it more advantageous to us. So to us, with reference to the capacity of the pump. So this just a presentation how a pump looks like in a pump room. And if you see, many of the tankers are having pump manufacturers. There are many of them. CISCO pump is very popular in many of the tankers. So if you see the range, capacity range here for an oil tanker, so starting from 1000 cubics to right up to 6000 cubic here, and of course total head, your head and your RPM. As you can see, higher the capacity, the RPM is of somewhere around 1100. I'll keep this pointer option like this so that I'll be able to. Okay, now the RPM is here. Shaft power, bore, weight. These are taken from the CISCO website. Very typical. Many tankers are having CISCO, yes, and the range of the capacity is given depending upon the size of the ship. And this, how to make the HQ curve, I think this has been discussed. It's just a hand-drawn diagram. You can just have a look at it. And the HQ curve is always in the y-axis. You have the head in meter liquid column, and x-axis you have Q. And we have somewhere here is a design point. And design point is the optimum design for which the pump is designed to deliver that much of Q or rate of discharge at the manifold, at the cargo manifold. And also you have the NPSH curve here. NPSH curve is always, it goes something like this. So what happens, suppose, let's say this is the discharge. If you throttle the discharge pump delivery valve, then what happens? Your discharge flow rate will reduce. So this will go like this. So when that's because you are creating some sort of a back pressure. So from here it will reduce. But when the flow rate reduces, you will notice when the flow rate reduces, what happens to the requirement, NPSH requirement? This also will reduce. Okay. Now, if required, we will come back to this diagram. But otherwise, the centrifugal pump curves for pumps just look like this. So this is what hand drawn earlier in the previous slide, HQ curve, and this is the power requirement. This is the design point. That's where you will find the efficiency being the maximum efficiency, and this one is your net positive suction head required. Basic concept of NPSH we have discussed in the last class, and when required, we will come back to the graph just to check. Okay, now if you see here, this is the concept of an oil tanker. So now this is the bulkhead between your engine room and the pump room, and the pump room is here. And the other side of the pump room, you have your cargo tanks, and this side of this is the bulkhead, supposed to be a watertight bulkhead between the pump room and the engine room. Now the engine room, you have the turbine. This is what we call COPT, cargo oil pump turbine. So this watertight bulkhead is having shaft. Your transmitting shaft is passing through because the prime mover. This is the pump COP, double bottom underneath. Nowadays, pump room also needs to have double bottom as per the present MARPOL Annex 1 requirement. So the pump is here and your turbine is here. And the watertight bulkhead, even though we not to have any opening there, but here we have an opening because the shaft has to pass through. Of course, we have to have seals there, bulkhead seals. And the location of the cargo pump is here. And you'll find there are pipelines on the suction side connecting to various tanks. Okay, now this is what we say. Nowadays, many tankers we have Vac Strip System. So this is a tank. So we will talk about Vac Strip System a little later. Now this gives you an idea. As you can see here, now this is the pump I am talking about, your COP, and COPT is right on top. This COPT is in the engine room, and COP is here. Of course, this is the shaft and the deck seal unit, what we call bulkhead seal. So bulkhead seal needs to have a integrity, because always, as we are aware, in tankers, what happens? The pump room, the atmosphere in the pump room has to be, the pressure needs to be slightly less than the atmospheric pressure, whereas in the engine room, it needs to be slightly above the atmospheric pressure. Because this sealing unit, what we call bulkhead seal, the integrity is very important. Suppose if there is any leakage, then the engine room, since the engine room is supposed to be at a higher pressure than the pump room. So if the pump room, in case if there is a leakage, what should happen? The engine room air may leak into the pump room, but it shouldn't be the other way around. So that's the reason the pump room, you will find we have a blower, an exhaust blower, and your pump room's atmosphere is always slightly less than atmospheric pressure. So this is about how the arrangement of in an oil tanker where you have COPs, cargo oil pumps, it is something like this. Now let me explain this diagram. Now here, what I have done is, now look at a cargo tank. Just visualize and cargo tank of an oil tanker. Now, what happens inside the cargo tank? You have, let's say, the tank is 3/4 full. You have already started commencing cargo discharge. So, inside the cargo tank, where do you mean? How much above the oil level? How much is the pressure there? Now, the pressure above, always the tanks are to be inerted. That means you are going to have some sort of an IG pressure. So, apart from inert gas pressure, what I am trying to say is, when the COP is running inside the cargo tank, you have oil level. Let us say the tank is 3/4 full. So, above the oil level, what you have alleged space. So, in the alleged space, you are going to have inert gas. So, that means what sort of pressure you have above the liquid level? You have atmospheric pressure everywhere. That is what is represented here. Now, here in this diagram, what I have drawn, positive and negative factors. So, if you see in a cargo oil tank, inside cargo oil tank, now this pressure, I am converting everything in terms of meter liquid column. Now, you see this is the atmospheric pressure. Now, this atmospheric pressure is everywhere inside, above the oil level, inside the cargo tank. Now, this atmospheric pressure is how much? We all know that atmospheric pressure is, how many meter liquid column. When you say atmospheric pressure is 1.0, let's take about, say, 1. So, if you convert it in terms of meter liquid column, you can say 10 meter. Theoretically, 10 meter liquid column, that is going to be the atmospheric pressure. So, atmospheric pressure I have converted in terms of meter liquid column, and I am representing it here. Okay, now these are the positive factors, and these are the negative factors which is going to affect the pump from taking suction. So, in this, what I am doing is, now this side is positive factors which helps the COP to take suction, and this side I have listed negative factors which will affect the pump from taking suction. So, let us, in the positive factors, I have written the atmospheric pressure, which is going to push the liquid down towards the pump eye of the impeller. Now the next line here, this is the IG pressure. Now, this IG pressure, how much is the IG pressure we have in oil tankers? IG pressure, generally we keep about, say, 600, 800, 1000 up to 1000. Somewhere around, let us say, 800 millimeter water column, or you can call it millibar. Now, that is the inert gas. So, now this is again a positive pressure which is going to push the liquid down towards the pump. Now, that is going to help you. So, the pump will take suction. But then if you see trim, always you must have seen, whenever we do cargo discharge, we always have trim by stern. So, now this trim by stern keeps increasing, and when during stripping time, you will find almost we go right up to 3 meters or 3.5 meters down by stern. So, now the trim is also going to help us. So, atmospheric pressure meter liquid column 10 meters I have written like this. Now, the IG pressure, then plus the trim, that is going to help the pump to take suction. So, these are the factors, this one, this line and this line. Now, this one is the liquid, that means this is the cargo to be pumped out. So, now I'm just, these are the positive factors. And if you see the negative factors here, in the negative factors, it depends upon the type of cargo what you have inside the cargo tank. Now, let me just ask you, suppose let us say a fuel oil, you are discharging fuel oil, let us say, you are on a product tanker and the fuel oil is at 60 degrees Celsius. Now, you are discharging that cargo. Or you are having another cargo, the cargo is naphtha. So, the naphtha or fuel oil at 60 degrees Celsius, where the pump performance is likely to be affected. When the pump is dealing with fuel oil at 60 degrees or naphtha at normal temperatures. So, gentlemen, can you answer? Any one of the participants? Hello?
What is the question? Sorry, sir.
So, the question is, when your COP in a tanker, when it is dealing with the fuel oil, it is discharging fuel oil at, let us say, 60 degrees heated fuel oil. And the same pump is handling naphtha or that type of cargoes, where the pump is vulnerable to loose suction, or where the performance of the pump
naphtha.
Naphtha. Why do you say naphtha is
Because naphtha vapor pressure will be more when compared to the fuel oil. So NPSHR will be a little bit come down. So liquid oil will be lost there.
Yes. So you are right. So if you see naphtha has got a higher vapor pressure. So here vapor pressure indirectly, what does it reflect? It talks about the volatility of the cargo. So the vapor pressure, that is what I have written here. Suppose if you see the negative factors, what I am writing here, VP means what? Vapor pressure. Now the vapor pressure of the cargo is going to be on the negative side. So if it is a higher vapor pressure cargo, you need to be more careful. So this vapor pressure, we will not be able to alter it. It is a nature, like as we have seen just now. The vapor pressure of naphtha is much higher than vapor pressure of fuel oil. Or it is, suppose if you compare between diesel oil and petrol, the vapor pressure of petrol is higher than the diesel oil. So that indirectly reflects volatility. So now this is your vapor pressure of the cargo that is being discharged from the tanks. And this one here, what I have written here now, this line, again, I'm converting this vapor pressure also in terms of meter liquid column. Now here, this is what we call line friction. So line friction means, see the pump performance, will it get affected when the viscosity varies?
Yes.
If suppose if the cargo is very viscous, you will find your centrifugal pump will find it difficult. So the cargo needs to be heated. So see, just compare, the viscosity affects the pump performance. So what else? Suppose the COP is running, let us say discharging from a cargo tank which is just next to the pump room. Whereas when it is drawing oil from number one cargo tank right forward, that means the length of the pipe or the diameter of the pipe, viscosity of the oil, or the number of bends in the pipeline. All these things, give some sort of, you can say, suction losses. So before the liquid reaches the eye of the impeller, these are all factors which is going to give some sort of a resistance, giving some sort of an obstacles before the liquid reaches to the eye of the impeller. Because as we have seen earlier, unless otherwise a proper priming is done, unless otherwise the pump is filled with the liquid, the centrifugal pump will not be able to perform. So on the negative factor, one point what I am talking about is the vapor pressure of the liquid which the cargo pump is handling. And the second point what I am looking at is a line friction. So now this friction depends upon viscosity, length of the pipeline, diameter of the pipeline, and other number of bends the pipe has got. It may be a short bend, it can be a long bend. So these are all the things contributing to this line friction. And apart from these two, then the next point what is there on the negative side is your net positive suction head required. Yes, we have seen in the basic part 1 of this program that net positive suction head required. That means every pump manufacturer will give a certain NPSH requirement. So as long when you are using it on board, as long as the available net positive suction head is more than the required, then your pump performs. Otherwise, you are going to have a problem. So now this is the requirement. So these are all the negative factors, and these are all the positive factors. Now what I am doing is I am comparing both. I am just drawing a dotted line just like this. Now that means if you just see, your positive factors are more. So as and when the COP is running, by the time this quantum of cargo discharging is not a problem. So initially the liquid level is so much, but later what will happen? Slowly it will keep on reducing. At one point you will find positive factors and negative factors on the inlet side of your COP will be same. Now that is the time we call it a critical point. Now what is going to happen? Now the pump may lose suction, or that is the time when cavitation will start. And what is cavitation also we have already discussed, all of you are aware. So now what we need to do to keep the cargo pump going, doing a good performance is, again, we need to make the positive factors little more than the negative factors. Now let us see, atmospheric pressure. Can we increase atmospheric pressure? Practically, it is not possible, because atmospheric pressure is constant. So if you increase the atmospheric pressure, you will get a benefit here, but you cannot do that. Of course, inert gas pressure, can you increase? Yes, very little you can increase. So you can, if it is already, let us say 600 or 800 millimeter water gauge, you can go, let's say 1000. But again, we have limitation. We cannot keep on increasing. So likewise, your trim also is the same thing. Trim, okay, 3 meter, 4 meter. How much more you will go? So you have a limitation here. There may be a very, very slight advantage here to have little more oil getting discharged by the COP. But if you see on the, either you have to increase the factors here, or what you need to do, you come to the negative side. Now vapor pressure can be reduced. If you reduce these factors, again we can look at the pump performing well. But vapor pressure is again like atmospheric pressure. We don't have any control over it, and you will not be able to reduce it. So if you reduce this, that's going to be of help, but you cannot do that. Of course, line friction can be reduced, or NPSH can we reduce? Can we reduce these factors? So gentlemen,
NPSH.
yeah, I'm just looking for some sort of an interaction here. Can we reduce line friction and NPSH required, gentlemen?
NPSHR can be reduced.
NPSH required can be reduced. Yes, that means we can have a reduction here. What about line friction? Can we reduce line friction? I told you, line friction you can say is the main factors are viscosity, length of the pipeline, diameter of the pipeline, number of bends and all that. Will we be able to reduce line friction? If you reduce this also, it is advantageous to us, isn't it? That means more oil will go. Can we reduce line friction?
Yes, sir, we can reduce line friction.
Line friction cannot be reduced. It is a function of length, diameter, and velocity of the fluid.
Yeah. Velocity
Sir,
of fluid.
if we use the cargo, then we can decrease the line friction.
Yes. See, since you say velocity of the cargo, see what you can do, line friction and the net positive suction head required, you will be able to reduce. Because if you see line friction is, you can say it is directly proportional to flow velocity. Am I right or wrong? Flow velocity. That means that's what you said just now, flow velocity. So how will you reduce the flow velocity? Like for example, your COP, you are running your COP at, let's say, 1200 RPM. So from 1200 RPM, so now people from tankers, you all know, when we are reaching on board a tanker, when you are discharging cargo, when you come right down to the stripping level, what do we do with the RPM? Do we reduce our RPM?
Yes, we reduce our RPM.
You reduce the RPM. So that means what will happen is, as I have said, line friction is proportional to flow velocity. So flow velocity, that means when you flow, that means when the pump RPM is reduced, then your flow velocity is reduced. Flow velocity is reduced, line friction is reduced. So here you will be able to reduce it. And when you reduce this line friction, again, if you just look back in the NPSH curve, what I have drawn, hand drawn in the previous slide I showed you, there again, when you reduce the RPM, your NPSH required also will get reduced. So by reducing these two, that's the reason we go in for, when we run our COP, stripping level beyond, we reduce the RPM. By doing so, again, you will have an upper hand here. You will have your positive factor of COP on the suction side more. So again, you will be able to comfortably go much closer. Of course, the last part of cargo discharge, we switch over. Yes, we may have stripping pumps, steam-driven stripping pumps, or we may have a Vac Strip System. Vac Strip System. Now, whatever I have written, whatever we have discussed, the same thing is given in a different format here. Now you see. Now, when the tank is full, since I have already explained in the previous slide, I think understanding this diagram will be much easier for you. So here, full tank is full, maximum discharge rate. So what are the factors we considered? Atmospheric pressure. You can see here atmospheric pressure, and then liquid column. This is your suction head. Now this is so much of liquid you have, and atmospheric pressure. Of course, IG pressure is not separately shown here. IG pressure, of course, I told you the trim also helps you. Whereas this side you have pipeline losses, vapor pressure, and the required NPSH. So when you compare these two, now here you can see what is written here, available pressure. That means coming right up to this much, this is the quantum of cargo that you have in the cargo tank. So this is a liquid column. So discharging up to this level is not a problem. Once when both these things are equal, then what you need to do, as I have told you just now, by reducing the RPM, you are reducing NPSH required as well as pipeline losses. Again, you see, vapor pressure, you will not be able to do anything. So by doing it, again you are reducing it. So you slowly come down, you try to empty out the tank. Now this is what is shown here. When is a critical moment where there is a possibility of cavitation occurring? So if you see here, atmospheric pressure is shown again here, critical moment, same discharge rate. That means you are continuing same discharge rate, meaning that your COP is running at the same RPM. Now this is your atmospheric pressure, no change. And this much quantum of cargo already you have discharged. Yeah? Now you have only this much cargo to go. And then if you see this side, now the pipeline losses, same. And in fact, the same thing here, because the discharge rate is not changing, you just take this and put it here. So that means both are same now, same discharge rate. Now this is the critical moment where the pump may lose suction, cavitation may occur. Now, if you continue at the same discharge rate, you will not be able to continue discharge. Then your pump will be running and cargo will not be coming out. So what is the best thing we do? Reduced discharge rate. Now this reduced discharge rate, what do we mean? As I have told you just now, have a look at the RPM and then reduce the pump RPM, which generally from the CCR, cargo control room, what do we do? Of course, we have a knob there. We reduce a knob, so that controls the governor, the speed governor, which sends steam to the turbine. It's your COPT. So now this is what is done. So now pipeline loss is reduced because of the discharge rate, and NPSH required is also reduced, and your available pressure is here, so that you will be able to complete the cargo discharge without any issues. So same thing. If you see this one, I have explained, and it's the same thing shown here. So I hope you have understood. If there is any other any questions, you can ask me.
Sir, this vapor pressure also can be adjusted using your temperature, no, sir? If suppose we are carrying heated cargo.
But by how will you reduce? Vapor pressure, you will not be able to reduce. See, by increasing the temperature or decreasing the temperature. Let me ask you a question. Now you see, diesel oil you take and petrol you take. So
Okay,
you bring 1 liter of petrol and keep it in an open space. Same thing you do with 1 liter of diesel.
Okay.
Then what will happen? Your petrol evaporates faster, no? So the property of the particular oil getting evaporated at a faster rate. That's what I said, volatility. So the temperature will not be able to change the vapor pressure. Okay, if it is very high temperature, probably it evaporates faster. That's what will happen. Otherwise, the property of vapor pressure, you will not be able to have any control by increasing the temperature or decreasing the temperature. Evaporation will increase or decrease, agreed. But then the nature of that property of volatility, that you will not be able to control. So the centrifugal pump. Okay. Now from there, let me come to the. Yeah. Yes. Any questions?
Sir,
I thought somebody was asking me any question.
Yeah, I think there is one person by name Elcott. Yeah, please, you can ask your question.
Sir,
yeah, please.
When we are getting a critical time, if we close our discharge valve, at the time we will reduce our flow rate. At the same time, we will reduce our friction loss, no, sir.
Yes. That also can be done, but the recommended procedure is reduce the RPM. See, the throttling the delivery valve also can be done, but throttling the delivery valve and the pump is running at the same, your rated RPM of about 1400. That is not recommended. So the recommended is, yes, what you say is right. Theoretically, by throttling the delivery valve, yes, you are reducing the NPSH required. You are controlling it. But then, if you are from a tanker, so on board tankers, what do we do? First thing, we reduce the RPM. So yes, the throttling the delivery valve is not a recommended procedure. It can be done for fine tuning at a later stage. But initially, first thing what you need to do is you have to reduce the pump RPM. That makes it much easier. Is it understood?
Okay, sir. Thank you, sir. Thanks so much.
Okay, now
Yes, sir. Thank you.
this, let me just look at the Vac Strip system. Now, this is for an, this is the cargo pump, what you have seen. This is the COPT and COP, and this is the cargo tank where the oil level is so much, and the suction bell mouth. And see what happens when the level comes right down, apart from throttling apart from reducing the pump RPM, some of the tankers or many tankers, they have this Vac Strip system. Now, this is where we have a separating tank, this is on the suction side. So, one thing what we do is, now right on top of the separator, by having these vacuum pump units right on top, you can just generate some sort of an under pressure. So whenever you do this, at that point of time, what is happening? The COP RPM is reduced, and the throttling side regulating valve is not fully closed, just throttled a little bit, and the RPM is reduced, and you run the vacuum. This vacuum pumps, I think even emergency fire pump we have it, or any of the central priming unit we have a vacuum pump. So now this vacuum pump will keep extracting the vapor or creating some sort of an under pressure at this point in the separating tank right on top. So because of the under pressure, what will happen? Now this pump is running with the delivery valve throttle. So because under pressure here, now the cargo here will be sucked in, and then this level of cargo will keep rising even though the pump is running. The outboard, the discharge going out is very much limited. So this level will keep on increasing. So you have a level controller here. So once the level reaches the set point here, then the stripping pump will stop. So what is the idea behind? Because you are transferring oil from this tank to the separating tank and raising the level of oil here in the separating tank. That means your COP will have a positive suction head. Once the level is reached here, when the vacuum pump stops, then the pump with the delivery valve open more or increasing the RPM, this oil will get discharged to the shore tanks. So now this is what we call Vac Strip system. In many tankers, we have this arrangement. But if you are looking at, now we have looked at the negative side. Now let us look at the inlet side. Now let us look at the discharge side. Now let us say the cargo has come right up to the cargo manifold. Now beyond the cargo manifold, that's where your chickson is connected, or your shoreline is connected, or loading arm is connected. Now once the loading arm is connected, you will notice from terminal to terminal there is going to be a difference. In some terminals you will find the shore tank maybe at a higher elevated position compared to the ship, or maybe at a distance, whereas in some terminals it's very close. So this shore curve, this is what we call backpressure curve. Now compare the shore curve 1 with shore curve 2. Now this is one pump. We are running one pump at let us say 1000 RPM. And when the cargo level goes down, and if you are not able to maintain the discharge pressure at the manifold, then probably we would have started the second pump. That means when the second pump runs in parallel, please understand, when two pumps run in parallel, the RPM of both the pumps should be same, 1000 and 1000 here. So now what has happened? The discharge rate has increased. But if the shore curve or back pressure curve is shallow like this, then what will happen? The discharge rate has gone from Q3 to Q4. Whereas in some terminals, in case if the shore curve is steep like this, you may come across, not this steep, just for discussion we are discussing here, or it may be something like this. So then what will happen? Earlier it was Q1, now it is Q2. But sometimes when we are running more than two pumps also in parallel, so we need to make sure, suppose when you run the third pump, is there going to be any increase in flow rate? If it is not so, then there is no point in running the third pump. So the parallel running always, we do it just to maintain the right pressure at the manifold. And this is the basic concept of your shore curves, Vac Strip system. So gentlemen, any questions on this? So that let me move on to chemical tanks. Chemical tankers, basically, in a chemical tankers, we are going to look at Framo system.
Mr. Sekhar, sir, moderator
Yes.
here.
Sure.
Yeah. Yes.
Polling time can inform the candidates. Dear participants, please give your valuable feedback by polling which appear in your screen. Thanks, sir. And no chats, no questions in the chat.
Okay.
Thank you, sir.
Okay. Now polling can keep, it can go on. In the meantime, I keep discussing. Now, gentlemen, now look at this. In a chemical tanker, we always have a Framo system. Now, see, if you see in this, this is the double bottom tank, and this is the cargo tank, and you are going to have the pump right here, right at the bottom. That means inside the tank, it's going to be something like this. I think this gives a idea. Now, this is your pump. The pump is here. This is your hydraulic motor. And if you see here, the pump, single stage centrifugal vertical pump. So the biggest advantage of this type of pumps, especially, what is the advantage? Nowadays, not only chemical tankers, we have it in product tankers, and some of the crude oil tankers also, I understand we have it. And the biggest advantage of Framo pumps is, first of all, you don't have a pump room. That means one less hazardous area. That because pump room is considered as a gas area. That means one less hazardous area. Okay. Now, apart from that, that much volume of the pump room can be used to lift more dead weight. That means more cargo. And also, the biggest advantage here is the pump is here. See, now this is the suction bell mouth. Since you have a double bottom at the bottom, you can afford to have a suction bell mouth, and the pump is located here. So, the pump is going to have always positive suction head. Now, think about your net positive suction head required. That issue is not going to be here. Still the tank becomes empty, the pump is going to have all the time positive suction head. So now this pump, Framo pump, if you are looking at, this is how it works. This is how it looks. It's a very simple diagram, and the pump is here. The cargo will go all the way right. This is the discharge pipe going all the way. Now you can see a discharge valve here. Now you can have discharge valve. And this is what we call stripping line, and this one is what cofferdam purging line, and the red line what you see there, now that is the pressure line. You see your hydraulic oil, we have a hydraulic system. The hydraulic system is like this, and we have a variable displacement pump, what we call power pack. Now this power pack can be either is in the engine room, or it can be on the deck also. I have seen some of my ships, we had it in the poop deck, or maybe forward of your ship also you may have, or you may have it in the engine room. So now, if you see this, the red line, the red is pressure oil. Now this pressure is going to be somewhere around 180 to 240 bar. It varies. In your ship, you need to see. In some of my ships, I had right up to 140 bar, 240 bar. Now, from this is the pressure manifold, and this is the return manifold. You know that green line, what you see, that is the return line. Now, from here it goes all the way. And where is the pump? Pump is here. Now this is at the bottom of the tank. So now from here, pressure oil enters and goes all the way to the hydraulic motor, and which the hydraulic motor, now here, now this is the hydraulic motor. So your pressure oil goes all the way, rotating the hydraulic motor. So the pump shaft rotating, so impeller is rotating, so cargo is getting discharged like this. And the yellow line, what you see here, now this yellow, that is the return oil. Now the pressure here is about, say, 200 bar, driving the hydraulic motor. And this oil, after having done the job, the return oil is about 7 bar pressure. 7 bar, it is going back. Now this oil here, this is the green line. You will notice one thing. Now this return oil is coming all the way, and in this return circuit, you have a filter, you have a cooler. You can see a cooler there, you have a filter there, and then it comes back to the pump section. Of course, you have a header tank, and in the header tank, hydraulic oil tank, we call it, we have a feed pump which is all the time running, even when you are sailing, or people generally we call it jockey pump. So, but here, if you see right at this particular point, now this is the shaft, and you have 2 seals here. This is the single seal. We call it cofferdam seal, and these are all made out of Teflon. Now this entire thing, pipeline, shaft, and the pump impeller, pipelines, everything is made out of stainless steel. Okay. Now here, in this line, the red line is your pressure oil, yellow is return oil, and here the blue line, what you see, that is what we say we call it cofferdam. This is supposed to be empty space here, empty space. And in case if there are seals here, there are bearing, everything is there. Suppose if there is any hydraulic oil leak off, that will leak into this cofferdam. Or if cargo, due to the, see now so much cargo is there. Now due to the static head, in case if the lower lip seal is leaking, then cargo will come to the cofferdam. Now this needs to be checked every time before you commence cargo discharge. Now that's what we are doing it. So here you can pressurize, you can put a inert gas or compressed air can be pressurized at this particular point. In case if there is any leak of oil will be here, it can be oil or cargo, whatever it is, and that will be pushed out through the small line. This is what cofferdam purging line, and here you can collect and you can see the integrity of the lip seals. Now this is the base concept how Framo pump works. But here what happens, now this oil level, this cargo level, when it keeps on going down, at one point of time you will find this level goes right down. Then that means the pump will lose suction. But you have still cargo only in the discharge pipe. If you stop the pump, what will happen? The cargo in the discharge pipe will fall down. So at that point of time, what do? We let the cargo fall and then close the discharge valve. After closing the discharge valve, again you start the pump. The cargo will fill here, and you see now this small line, the skipping line has got a valve here, and this valve is open. This valve is closed. Then with the compressed air, you can just blow through this line after the valve. This valve is closed. This line is depressurized, and then again this small valve can be opened with the pump running with a connection here. See this particular point where we connect compressed air or IG or nitrogen in the case of chemical tankers when required, and that means you are pressurizing this tank. But this cargo cannot go into the tank because the impeller is running, because your pump is running. So then where the cargo will go in the discharge pipe, that will pass through the small diameter line here, what we call skipping line. And since this valve is open, it will come after the valve and it will get emptied out. Now this is what we call stripping. So this is the arrangement, and you can just have a look at of course, the necessary bearings and mechanical oil seals, all those things we are having. And also here we have an anti-rotation brake. You can see the anti-rotation brake at that particular point, which will prevent the pump from rotating in the opposite direction. Because sometimes what do we do? In chemical tankers, we do even loading through this pipe. If you don't have a drop line, and if cargo loading is done through this, then what will happen? There is a tendency for the impeller to rotate in the opposite direction. So that this anti-rotation brake will avoid. So this is how a Framo system that we use in chemical tankers. So now here it's a very simplified diagram where you can see the hydraulic oil tank. This is a header tank, and your power tank, which is driving the high pressure hydraulic pump. And you can see the red line, manifold, pressure manifold, and diverting to all the cargo. There is one cargo pump here, there is another cargo pump. It will spread around. You may have product tankers or chemical tankers, you may have more number of cargo tanks. And the return line is that yellow line. Now the yellow line, through that, it just comes back to the pump. So this is how a chemical tanker cargo pumping arrangement is there. So any questions in Framo pump, gentlemen? Just a basic concept.
So the use of the purging line, cofferdam purging line.
Cofferdam purging line is, as I have said, now this is the purge pipe. Now see the arrow where I am showing you. This is the purge pipe. The idea of purging is just to find out the integrity of the seals, whether the seals are holding, or if the seals are leaking. I told you, either the hydraulic oil will leak into the cofferdam or cargo will go. If the upper seal is leaking, you see here, in case if this seal is leaking, what will happen? Hydraulic oil will leak. Suppose if the lower seal is leaking, then cargo will leak. Now this is your cargo. So every time before commencing cargo discharge, what do? We always do pressure. Your cofferdam. We just purge it just to make sure that there is nothing here. But a small quantity, if it is there, you can see your Framo guidelines. Small quantity is allowed. And again, after cargo discharge is over, again we do the purging routine. Now, purging routine, Framo has come out with a very specific guidelines and the format, how it is to be done. So basic concept, why we are doing it, we are just checking whether the cofferdam here, the empty space, it's supposed to be empty. There is no, it just to check the integrity of the seals, we are doing purging routine. And in case if you find more of oil or cargo coming, then that gives us an indication that that particular seal is requires attention, and first opportunity we change the seal. Does it answer my question? Your question?
Yeah, understood. Thank you, sir.
Okay. Now it's again the same thing, but as you can see here, it's a normal, it's a single stage centrifugal pump, and of course the bearings are shown, and this is the cofferdam what I have just mentioned about. And shall we move on to the gas tanker cargo pumping arrangement? So if you see in a gas tanker generally we have this is your cargo pump, and this is your drop line, and your cargo pump, as you can see, it's a 3-stage centrifugal pump. See, the biggest problem here in cargo pump in a gas tanker is what? It's a liquefied gas. Liquefied gas means, okay, you have liquefied it, it's in the liquid form, so the centrifugal pump must be able to handle it. But always there is a possibility of cargo turning into vapor. If cargo turns into vapor, it's going to be an issue. It's going to be a problem for centrifugal pump. So, as you can see here, it's a single shaft coming like this, and you have a first stage impeller, then the first stage, see right here at the suction bell mouth, you have an inducer. So this inducer you will find only in gas tanker cargo pumps. As you can see here, inducers fitted to the pump impeller. What is the purpose of the inducer? To ensure there is sufficient supply of fluid at the impeller, avoiding cavitation at impeller suction. Or in other cases, in other way, you can say the suction losses are averted. You see the profile of the inducer. So when the shaft is rotating, inducer also will rotate. So it will suck the liquid and then turn around through this profile, and it makes the suction losses less. It allow the pump to operate with a lower net positive supply head. Now that's the reason they are given the inducer. Then it enters the first stage impeller. Discharge of first stage impeller goes to the second stage suction. Second stage discharge goes to the third stage suction. And again, now this is your discharge pipe, and then it just goes all the way up. And then if you see this is the shaft, and always the prime mover here is an electric motor, or you can say approved type of electric motor. I think this diagram, you have a very clear picture here. Now this is your approved electric motor, and of course as you are aware, your gas tanker cargo arrangements and everything, construction, everything is governed by IGC code. So IGC code gives very specific requirement how the motor should be. It should be non-sparking, intrinsically safe motors, approved type of motors right on top. And this is your discharge valve, and then this is the discharge pipe where it is going to the manifold. Or here you can see a schematic diagram, the inducer, of course bottom bearing here, and of course bell mouth, suction bell mouth, and 3 pump stages. And this is a rotating shaft, and the liquid cargo goes all the way here, and then here it comes out and going to the manifold. Now here, what I have drawn X-axis, because if you have a long, see the, what will be the height of the tank? Let us say 20 meters or 18 meters, whatever. We can't afford to have a long shaft about, say, 20 meters, driven by a motor, outside on top of the tank. What will happen? Some sort of a wobbling possibility is there. So to stop that, within the discharge pipe, at specified points, they have something like this, what they call intermediate bearing. Now, this intermediate bearing, if you just look here, now this is the rotating shaft, and it has got a bearing housing, and then there is a bearing there, and this is the discharge pipe, and through the discharge pipe, the cargo will be going all the way up. That means here, there is a bearing. Now, this bearing is going to be around the shaft. Shaft is rotating, and this bearing happens to be the carbon bearing. Now, this bearing lubrication is done by the cargo itself. So, it is very, very imperative that this pump should not run dry. So, when the pump is running, the pump has got a certain amperage, rated amperage. So, at the end of the discharge, when discharge is over, when the pump, the cargo quantum has reduced, then what will happen to the amperage? The amperage also will go down. So at the minimum amperage, the pump will get tripped, so that prevents the pump from running dry. So this is how a deep well pump is going to be. And some LNG ships you may see a cargo pump like this, and very often they also call it, spray pump or stripping pump. So here the arrangement is slightly different, because in this type we saw the motor right on top and the pump elements here at the bottom of the tank, something like this. Now this is your 3-stage pump. Whereas in this arrangement, you see the motor is also here. So this is the stator, this is the rotor, and this is the junction box, and the electric cable is coming all the way, and this is connected to the motor, and this is the discharge pipe. See, pump discharge here, I think you are able to see here. Pump discharge is going all the way. So the pump inlet side, so the liquid enters here, and this is the pump impeller. So the cargo flows all the way through the, you can see the pink color arrow. The cargo flows, and through the discharge pipe, it goes all the way. So this is